Okay, hi everyone. In this lesson, we will learn that we can use average bond energies to approximate the change in enthalpy of a reaction, which is delta H of the reaction. Let's consult our textbook. In our textbook, we can find this table, which is in Chapter 8, and take a minute to study what this table is showing you. Hopefully after a couple minutes, you've noticed that the units here are kilojoules per mole, so this is energy somehow, and that all of these values are positive. So what does this mean? What does this tell us? Well, these are bond energies. So if these values are all positive, then this is the energy required to break these specific bonds. Energy needs to be put into the bond in order to break it. I can think about it like a stick. If I try to break a stick, I need to put energy into it if I'm going to break that stick apart. So the same thing is here. All of these values are positive. I also notice here I have multiple bonds. I have double bonds and triple bonds, which require more energy to break. I also notice a little exception down here, a little asterisk that I want to pay attention to, and this is for the CO bond in the carbon dioxide molecule. This will require 799 kilojoules. So I want to pay attention for that if we have anything, if any CO2 show up in our examples. The other thing to note here is that these are averages. If I look at the CH bond, which requires 413 kilojoules to break, not every CH bond is exactly the same, and so 413 is an average. Just be okay with it. It's an approximation. It's still useful to us for what we're going to do here. Another table I should find is this, bond lengths for selected bonds. And this shows the relationship between bond length and bond energy. I notice with my single, double, and triple bonds that my length, measured in picometers, gets shorter. The bond energy, the energy needed to break those bonds, gets bigger, so more energy is needed to break those bonds, which kind of makes sense because in a triple bond, then those atoms are going to be closer together, so more energy is needed to break them. Okay, we'll come back to this table in a little bit. Let's do an example. So if I switch over here, here's my first example. I have hydrogen reacting with oxygen to form water. Another way that I can write this instead of using symbols is to draw out these molecules. And so this is a good review of Lewis structures. I have two H2 molecules reacting with one oxygen molecule, which has a double bond, and I form two water molecules on the product side. Let's take a minute and look up each of those bond energies from the table. So HH is right here, that's 432. O double bond is 495, and I have an OH bond which is 467. So let's see what we're going to do with those numbers. I want to take into account all of the energy being put into breaking those bonds, and I want to know all of the energy that will form the bonds. So I can do this. I'm going to take my 2 moles, because I had 2 hydrogen bonds that I was breaking, times the 432. That was from the bond energy for breaking one bond between HH. I'm going to add that to 1 mole times 495. This was the value for breaking the oxygen double bond. And I could do 2 things here. I could add the negatives of these, because if those are bonds being formed, then I'm just going to flip the sign on those. But I could also subtract the actual positive values. So I'm going to do that here. I'm going to take 4 moles, because I was forming 4 OH bonds, times the 467. So that will simplify and reduce down here. So 864 plus 495 minus 1868, make sure you're getting those same values, will equal negative 509 kilojoules. So what does that mean? What does that tell us? It tells us that this reaction is exothermic. It also makes me point out that water is a compound being formed from its elements. And so what you've really found here is an enthalpy of formation, which isn't the standard enthalpy of formation, but it's related, because you formed 2 moles of water here. If I look up again what those delta H's of formation are, For water as a liquid, it's negative 286, and for water as a gas, it was negative 242 kilojoules. If I divide negative 509 by 2, I get negative 255. So I'm in the ballpark here between these two values. And that's okay because remember, these were averages that I used up here. It's still useful because it tells me generally, if I'm in the ballpark and if it's endothermic or exothermic. So what I've got here then is this summary so far. Bond energies are averages, and we can use them to approximate the delta H of a reaction. Let's see another example. So in this example, I have a molecule of methane reacting with 2 molecules of oxygen to form carbon dioxide and water. Hopefully I'm recognizing this is a combustion reaction, so what you're really finding is a delta H of combustion. Same thing as a delta H of a reaction. I'm going to draw out all of my structures. So I have a methane molecule, I have 2 oxygen molecules, each with a double bond. I'm forming 1 CO2 molecule, and I'm forming 2 water molecules here. Take a minute and look up those bond energy values from the table, and we will tally up all of our bonds here. So I've got 4 CH bonds, 2 O double bonds, 2 CO bonds, and remember this is from the CO2 molecule, so use that value when you're looking it up in the table, and 4 OH bonds. Take a minute and look those up. Once you've done that and you come back, hopefully we came up with these same values. I'm going to take 4, because of the 4 CH bonds, times 413, plus 2 moles, 2 O double bonds, times 495, minus 2 moles, times 799, hopefully you use that exception value, plus 4 moles, times 467. So remember again, this is all of the energy being put into breaking the bonds minus all of the energy forming the bonds here. So I should end up with negative 824 kilojoules. What does that tell us? Again, that tells us that this reaction is exothermic, which makes sense because it's a combustion reaction. We know that those are very exothermic. They give off large amounts of heat and energy. And yeah, this value is large here. Not as large as it would be if it was a bigger carbon molecule, but this is good for now. So in summary, what we've done is, again, we've used bond energies as averages to calculate the delta H of a reaction. That can be summarized using this formula here. Delta H is the sum of D broken minus the sum of D formed, where D is the bond energies. So all the energy going into breaking my bonds minus all of the energy forming the bonds. Okay? Thanks for watching today's video. We'll see you back in class.